Welcome to everyone. My name is Noussaiba Mennai. I am a PhD student at the University of Skikda, Algeria. I am very grateful to be part of the multi-conference SSD 2022. On behalf of my co-authors, I would like to present our research paper entitled Grid Synchronization Techniques Analysis of Distributed Generation Systems under Grid Fault Conditions. These are the main parts of this presentation. The integration of renewable energy sources to actual transmission power grids around the world has recently gained a significant penetration level. The changes brought by these alternative power sources have an important impact on system performance and efficiency in terms of the quality and the stability of the existing grid, which is not yet dedicated to meet the modern grid code requirements. For safety and reliability of power systems based on the distributed generation system, power plant operators have to satisfy grid code requirements, such as grid stability, fault ride-through, power quality enhancement, power control, and grid synchronization, etc. One of these vital requirements is the synchronization with the grid voltage, which is achieved by the synchronization unit of the grid-side converter controller. This unit usually consists of a phase-locked loop PLL algorithm to track the phase angle and amplitude of the grid voltage at the point of common coupling PCC. So, the tracking of the phase angle accurately during normal and abnormal grid conditions is necessary to control the flow of active and reactive power, to ensure a unity power factor, and to generate gate signals to the inverter. As per the requirements, the phase-locked loop PLL must have the ability to work in both balanced and unbalanced grid conditions. The main contribution of this paper is to find an accurate synchronization PLL among these four techniques. The different considered algorithms were presented, analyzed, and compared, and their performance was simulated by using MATLAB SIMULINK environment. The comparison of their performance is carried out during the presence of a line-to-line-to-line fault and a line-to-ground fault. Modeling of PLLs. Starting with the conventional ones. First of all, what is a PLL? A PLL, as mentioned in the literature, it is a closed-loop algorithm which tracks automatically and regulates the phase of a generated signal to be equal to an output signal. It is composed of a phase detector, loop filter, and voltage-controlled oscillator. First of all, the SRF-PLL, called also decoupled. This is the structure of it. In SRF-PLL, it starts by measuring the three-phase voltages VA, VB, VC. Then by doing a transformation by the means of Clark and Park transformation, we get to the synchronous frame components VD and VQ. An important aspect of this transformation is that the voltage of the D-axis VD has to lie on VA. This can be achieved by forcing VQ to be 0 by the means of a proportional integral controller, PI controller. Then by integrating the output of the PI controller, we get the theta decoupled. Then the modulo block here wraps it between 0 and 2 pi. Αβ-PLL. This is the main structure of αβ-PLL. It uses here Clark transformation. In αβ-PLL, we have the difference delta theta to estimate the phase angle by trigonometric equations here. Advanced three-phase PLL. We have DSRF-PLL. This is the structure of it. Actually, it is an improvement of the SRF-PLL. This is the SRF-PLL, and this is the improvement here. Why? Because when the grid is unbalanced, both positive and negative sequence components of the grid voltage appear. And because of the inability to regulate these components independently, we have to extract these components into synchronous reference frame, as mentioned here. DQ plus and DQ minus 1. DQ plus 1 and DQ minus 1. They are rotating in negative directions. When an unbalanced disturbance occurs, the fundamental positive sequence of the grid voltage vector appears as a DC voltage on the DQ plus 1 axis of the positive sequence SRF, plus an oscillation with 2 omega frequency, which represent AC voltages appear on the DQ minus 1 axis of the negative sequence SRF. On the other hand, the negative sequence voltage vector produces a DC component on the negative sequence SRF plus an AC oscillation term on the positive sequence SRF. To cancel out these oscillation terms, a decoupling cell, as mentioned here, is implemented. Actually, two of them. One for dq plus 1 and the other one for the dq minus 1 SRF axis. The DC components are obtained by the mean of low-pass filters here. The αβ-PLL. This is the main structure of it. This is the αβ-PLL. It is a combination of αβ-PLL plus with two decoupling cells, the same as used in the SRF-PLL. Moving on to the simulation results. These are the parameters used in the simulation. At 0.1 second, the three-phase fault will be applied and removed at 0.3 seconds. These are the four models of the four PLL techniques, and since a line to ground and line to line to line faults are the most common asymmetric and symmetric faults in the grid respectively, both of them are used in these simulation. Simulation of results of SRF-PLL during symmetric and asymmetric fault. Starting with the symmetric one, here it is clear that the phase angle and the frequency are well tracked by SRF-PLL during the symmetric fault or even in normal conditions. However, it fails in determining the grid voltage, phase angle, frequency and frequency under asymmetric fault. They are seen here with many distortions, simply because we cannot control positive sequence and negative sequence components of the grid phase independently. So moving on to simulation of αβ during symmetric and asymmetric faults. During symmetric faults, here it is similar to SRF. It can track accurately in both normal and symmetric faults. It can work very well. The maximum phase error is 0.127 radian, and the overshoot here is lower than the one in SRF-PLL. But here the same it cannot track the phase and frequency during unbalanced fault or asymmetric fault. They are seen here also with many distortions. In the DSRF-PLL, it is obvious that the asymmetric when asymmetric fault occurs, it operates the same as normal conditions. So it works very well even when there is a line to ground fault. Therefore, it has an improvement results compared to SRF-PLL. Here, because we obtained both positive and negative sequences independently, and the effect of the second order harmonic component VD and VQ voltages disappear. We have no distortions here. Also, there is no phase error in the steady state under this asymmetric fault. Furthermore, by comparing this the SRF-PLL with SRF-PLL, we can see that the conventional one responds faster than the decoupled one, roughly after 10 milliseconds. This can be justified by the fact that DQ-PLL has a simple structure. From the Dαβ-PLL results, it is clear that the Dαβ-PLL has also the ability to track the phase angle efficiently, even under asymmetric faults. As you can see, the positive sequences and the negative sequences voltages are well maintained. Also, the frequency is maintained to 50 Hz. By comparing the DSRF and the Dαβ-PLL frequency responses, we can conclude that the DSRF-PLL has a higher peak overshoot here in the blue one, which is undesirable, and the peak overshoot in Dαβ-PLL here is reduced by 16%. So the hybrid Dαβ-PLL model has better performance under balanced and unbalanced grid conditions compared to the other PLLs investigated earlier. Conclusion: after investigating the synchronization capability of the four PLLs, we can conclude that SRF-PLL and αβ-PLL algorithms can track the phase angle accurately only during normal conditions and symmetric faults. Also, SRF-PLL responds faster than the DSRF-PLL due to its simple structure. By comparing the two advanced techniques, the αβ-PLL has the best compromise between lower overshoot and phase angle tracking efficiency during normal and fault grid conditions. Even though the other techniques have good performance too and still can be used, but their choice should take into consideration their features, drawbacks, and if they suit the application purposes or not. These are the references used in this presentation. Thank you so much for your attention.